Welcome to Brain Vision.
In this problem, we're going to be looking at a hypothetical space station in orbit above the Earth. So that's the Earth here. It's sending a beam of electromagnetic energy up to this space station that's in orbit up here. And they've told us that the cross-sectional area of this beam, so if it's got, maybe a round shape or whatever it is, the cross-sectional area A is 135 meters squared, and the power that it transmits is equal to 1.20 times 10 to the 4 watts. And so knowing what that average power is and the area, what we're trying to find is the ERMS and the BRMS. So that's the root mean square values of the electric field and the magnetic field. So to get started, we're going to be using this equation. The average power is equal to average intensity times the area. Power and area we already know. So it's just a matter of finding out what that average intensity is. Let's start with the electric field, because the intensity has slightly different form depending on whether you're looking for electric or magnetic field. So in terms of the electric field, the average intensity is equal to C epsilon naught times the E RMS value squared. Using that, then we can just plug it right back in to our equation for the average power. P equals C epsilon naught ERMS squared, and then of course times the area. I'm just going to rearrange some of these terms around in order to make it clear that we're solving for the ERMS. So we can divide both sides to get E squared RMS is equal to average power divided by C epsilon naught times the area. Then just need the square root of both sides. We get E RMS is equal to the square root of the average power divided by C epsilon naught times area. And so this right here, we have everything we need to go ahead and start plugging in values for that and solve for the E RMS. I'll write that over here so we have a little more space. Square root, and what's the power? 1.20 times 10 to the 4 watts. Divide by, for C, we're going to use 2.9979 times 10 to the 8, and that's meters per second. For epsilon naught, we use 8.85 times 10 to the minus 12, and that's got units of Coulomb squared per Newton meter squared. So we plug those in here. 2.9979 times 10 to the 8, 8.85 times 10 to the minus 12, and then of course the area 135. Plug that into your calculator. It should all come out to about 183. And if we keep a close eye on our units, meters per second, coulomb squared per Newton, meter squared here. All of our units should turn out to be newtons per coulomb, exactly what we expect for the electric field. Next, let's take a look at the magnetic field. And we're going to do pretty much the same thing, except that we have a slightly different intensity that we're dealing with. So when it comes to the magnetic field, the intensity is equal to C over mu naught times B squared RMS. And so mu naught there is the vacuum permeability. Mu naught has a value of about 1.257 times 10 to the minus 6 units of henries per meter. So that's what we'll be using there. And then otherwise, this all works very much like in the previous problem. So we have our equation for average power is average intensity times area. Power and intensity hasn't changed, so we're just going to substitute in a different version of the intensity in order to solve for B RMS. Power is equal to C over mu naught B squared RMS times the area. And then we just divide by some of these other values to get them over onto the other side of the equation here. B squared RMS is then equal to average power divided by C over mu naught times A. We'll take the square root of both sides so that the root mean square of the magnetic field this time is equal to the square root of the average power divided by C over mu naught times A, the area. And just as we did before, then all we need to do is start plugging in our values. Using the same power that we had, 1.2 times 10 to the 4 watts. C is still the speed of light. Now we use our value of mu naught that we have over there, 1.257 times 10 to the minus 6. And then the area, which was 135 meters squared. Plug all that into your calculator, you're going to get something that's about 6.1 times 10 to the minus 7. And the units get a little complicated here, but since we're using all standard units, meters, seconds, watts, we know that the magnetic field is going to work out to units of Teslas.